In this lecture, we are going to talk about triple integrals. So now the integral is on an object in the space, three-dimensional. So we are going to have dx, dy, and dz. So f is a function defined on a rectangular box, which x sits between a and b, y is between c and d, and z is between r and s. Okay, we have this box or rectangular prism, and the triple integral of f over b is defined the same way. It's a limit of Riemann sum, where the box is divided into many small boxes. Okay, so along the length, the width, and the height, you divide each side into L, M, and N equal pieces. So the whole big box becomes L times M times N equal small boxes. Then L, M, and N all go to infinity, which means each small piece of the boxes get smaller and smaller and smaller. Then on each of the box you pick one point. Well, in each of the box, I don't mean the surface, I mean the whole thing. In each of the boxes you get one point represent the whole box. Then that point will be the x star, y star, z star. Then we multiply the value of the function with the volume of the box, which again, they're all the same, although all those equal volume goes to 0. But meanwhile, we have the number of boxes gets more and more. That's our Riemann sum, and when the limit is a number, if the limit exists, then our integral is defined. So same way, we divide intervals into smaller pieces for one-dimensional function. Then for double integral over a rectangle, we did this, right? We cut the rectangle into smaller rectangles. Now 3 dimensions, same thing, you divide it into smaller boxes. First example, evaluate the triple integral over the integral over box B of x, y, z squared dv, where b is 0, 1 cross negative 1, 2 cross 0, 3. That is the same as x sits between 0 and 1, y sits between negative 1, 2, and z sits between 0 and 3. They are the same thing. So our integral, because the region that we're, the domain that our integral is over, it's a box. So dv will just be 0, 1 dx, negative 1, 2 dy, 0, 3 dz, and then inside you have x, y, z squared. Okay, or if you prefer dx, dy, dz, then you will need to do this backward. If you want dx, dy, dz as sort of the regular way, then you will have to do the integral with z, 0, 3, then y is negative 1, 2, then x is 0, 1, then you do x, y, z squared. You need to make sure the outer limit and the differential are the same, and then the inner and inner, Because it's a box, actually it doesn't really matter which order you put with your dx, dy, and the dz. And if you want to, you can separate the thing into x, y, and the z part. So if I do it really like little by little, well, I'll do the way I wrote already. So I'm having the 0, 3, negative 1, 2, 0, 1, yz squared dx, then dy dz. Then I evaluate this part first. This will give me, oh sorry, I lost my x. So this will give me from 0 to 3, negative 1 to 2. Inside, I'm having yz squared as coefficient, 1/2 x squared. Evaluate from 0 to 1, then dy dz. This evaluate from 0 to 1 will be 1/2. 1 squared minus 0 squared, which is 1/2. So the thing will be from 0 to 3, negative 1 to 2, 1/2, I'm doing y, z squared times y, dz. And this will be from 0 to 3, 1/2 z squared times 1/2 y squared. Sorry, this is x, and this is y, goes from negative 1 to 2. And this will be, well, and dz. This will be 1/2, 4 squared minus 2 squared minus negative 1 squared. So this will be 3/2. Then the whole thing will be from 0 to 3, 1/2 z squared times 3 over 2 dz. And this is 3/4 times a third, z to the third power, from, sorry, z from 0 to 3. And this will be a fourth times 3 to the third power, which is 27 over 4. Okay, that is the regular way you do it, but also you can do it as 0, 3, negative 1, 2, 0, 1, x, y, z squared, dx, dy, dz, because the inner part, the integrand, is a product of x, y, and z squared. So you can really just do, well, let me use red so you know they're separate. This will be from 0 to 3, that's my z part, z squared dz times negative 1 to 2, y dy, from 0 to 1, x dx. So pretty much, if you remember how you get your integral little by little, this is the 1/2. This is the 1/2 x squared from 0 to 1. This is the 1/2 y squared from negative 1 to 2. And this is the 1/3 z third from 0 to 3. Okay, if you plug in the numbers, you will have exactly the same thing. I don't have room to show you, but yeah, they will be the same. Now, what if the region that we are doing our integral over is not a box? We do the same, we define it the same idea. We use a bigger box to surround it, to cover it, and then we fill in the extra space with function 0. Then we define our capital F. And the capital F, the integral of capital F over the bigger box is the same as the original function you are looking at, the lower f, in the really valid region E, because you fill in extra spaces with 0. So it doesn't, as integral, it's a sum thing. So it doesn't really grow by filling a lot of 0 in. But meanwhile, we have a domain. We have the region as a box. Now with this random region in R3, how are we going to convert it into an iterated integral so that we can compute the integral? Again, it's the same idea. So a solid region is set to be type 1 here. Notice this is not Roman number anymore. It's really number 1. Okay, type 1. If it lies between the graphs of two continuous functions, x and y. What it means is that, for each x and y value, you can have a function that bound the lowest z and highest z. Which means pretty much the z, upper z and lower z are sort of defined on the same xy plane, although they can have different shapes. For every x and y, you can express z. If that is the case, you are going to, so this is z. You go upward, you can, so this is xy. Z, the lowest z is u, whatever in terms of xy, u1, and the highest z is u2. If you are able to do that, then pretty much you get rid of the z dimension. You are doing the integral over your region area area D. Then you look at the D. How can you express D? Okay, if it's a type 1 function, that means for every value x, y is between two certain functions. And if you are having type 2, which means for every y value, x is sitting between two functions, then you go back to the 3-dimensional region. So pretty much this is the idea. You need to imagine when you project it on xy, which means along z, or you project it on yz, which means along x, or project, by it I mean the e, on xz plane, which means along y. When you smack it, the whole thing, you know how the boundary is in a way. And then the projection is your D region. Okay. And of course, let's try to do it with an example. Evaluate this integral over E of z dv, where E is the solid tetrahedron bounded by the planes x equals 0, y equals 0, z equals 0, and x plus y plus z equals 1. Okay, so first, what is the graph? We are having x equals 0, y equals 0, z equals 0, which are the xy, xz, yz plane. I don't think I said it as exactly the same order. X equals 0 is the other two letter, yz plane, okay. Yeah, and then x plus y plus z equals 1. You are going to have 1, 1, and 1. This is the fourth plane. So putting them together, you have this tetrahedron. So you pretty much have everything inside, okay? Now, how are we going to write this v? How are we going to express this v as a function? Well, not function, as an iterated integral. So I'm going to just imagine I push the whole tetrahedron down on my xy plane. What will happen? All I'm going to get is this triangle. Not only that, but for each of the xy pair, I draw a perpendicular line, vertical line. The lowest point inside V is z equals 0, and the highest point is where you hit the x plus y plus z plane, which is z equals 1 minus x minus y, because you're on x plus y plus z equals 1 plane. So first of all, you can collapse it on your xy plane. Second of all, after that is your plane, after you have the region which we call D, Okay, now this is my region D. Every xy pair, I know the lowest point is z equals 0 and the highest point inside my V is z equals 1 minus x minus y. And how about the D? How does it look like? Notice when you are going to graph it again, you sort of rotate this thing the other way around. So you need to, this is like you're rotating 90 degrees. Yeah, so the triangle is between the origin, right? That's the origin. This is 1, 0, 0. But for x and y, you are having x equals 1 and y equals 1, and this is 0, 1, 0. But when you are on the xy plane, you lose the z coordinate. So you are in this region. That's your D. Okay, so then you are going to express your D as your new region, and you are going to say the integral over D. I pick an x value. My x is between 0 and 1 for each xy value. My y goes from y equals 0 to, what is this point? This is y equals 1 minus x. Y-intercept 1, slope negative 1. So y goes from 0 to 1 minus x. Then I'll put everything together. The whole integral z dv is, first is the integral over d of the z part is from, let me use another color so you know where I get them, from z equals 0 to z equals 1 minus x minus 1. So from 0 to 1 minus x minus y, and then I put my integrand z dz. Okay, I get rid of my z dimension dA. Then I rewrite my a as my x goes from 0 to 1, and my y goes from 0 to 1 minus x. Then you have the 0, 1 minus x minus y, z dz, which was already there. And then this is my dy for, the inner integral. At the end, you have dx. So I rewrite my integral as this iterated version, 0, 1 minus x, 0, 1 minus x minus y, z dz dy dx. Although my integrand is only z, but because the domain of the integral is not a box anymore, I can't move it out. I have to do it from the inner to the outer. Now let's really do it. So I already converted my integral into, if you remember, 0 to 1, then 0 to 1 minus x, 0 to 1 minus x minus y, z dz dy dx. I need to do the inner part first. So 0, 1 minus x minus y, z dz. This is, of course, 1/2 z squared, where z goes from 0 to 1 minus x minus y. So this is 1/2 1 minus x minus y squared. And do I want to expand it? I'll expand it. Although actually, if you're not expanding it, it's so much easier. But I'll imagine most of you would expand it anyway. But here I'm not going to show you the whole multiplication. This is 1 plus x squared plus y squared minus 2x minus 2y plus 2xy. That's the sort of the perfect square formula for 3 terms. So I'm having 1/2 plus x squared over 2 plus y squared over 2 minus x minus y plus xy. Then I'm going to throw it in the second integral. So my original integral becomes 0, 1, 0, 1 minus x with this whole thing, x squared plus 2 plus y squared over 2 minus x minus y plus xy dy dx. Now I'm going to do this, which is dy. So do I want to copy it? Maybe I will. So 1/2 plus x squared over 2 plus y squared over 2 minus, well, let me copy it in another order. I'm doing dy, so everything that doesn't have y goes together. And then I'm having the y term. I'm having minus y plus xy, then finally have the 1/2 y squared dy, and that will be 1/2 plus x squared over 2 minus x times y, and minus 1/2 y squared plus x times 1/2 y squared plus 1/2 times 1/3 y third. Y goes from 0 to 1 minus x. So this will be 1/2 plus x squared over 2 minus x times 1 minus x. And these two terms will be do I want to put them together? I guess I do. Plus 1/2 x minus 1 times the y squared, which is 1 minus x squared, plus 1/6, 1 minus x to the third. The reason is I want to show you that I have pretty much the 1 minus x to the third, And this, if you pull out the 1/2, good, I have another color, 1/2, this will be 1 plus x squared minus 2x, which is 1/2 x minus 1 squared, or 1/2 1 minus x squared. So this whole thing becomes 1/2 1 minus x to the third power minus 1/2 1 minus x to the third power plus 1/6 1 minus x to the third power. Because when I change the sign from plus or minus, I change this from x minus 1 to 1 minus x, so that I have the third power. They cancel each other. I'm only having the 1/6 times 1 minus x to the third power. Okay? Now, I guess I will need to get rid of some sketch so that we can continue. Do we have room? I'm almost done. No, I still need more, so let me just get rid of this. Okay, so I just took away the calculation of my second integral, but I already showed you that this integral will end up with the 1/6 1 minus x to the third power. Now bring it to the outer, the last integral, 1 minus x to the third power dx. This is where I'm not going to really introduce the new variable, but dx, I'm going to need d1 minus x, right? So from 0 to 1, dx is negative d1 minus x. Then I have 1/6 1 minus x to the third power times, so this will be negative 1/6. From 0 to 1, 1 minus x to the third power d1 minus x. And this will be negative 1/6 times a fourth 1 minus x to the fourth power, x from 0 to 1. And that is negative 24. X equals 1, I'm having 0 to the fourth power. X equals 0, I'm having 1 to the fourth power. So this will be negative 24. Sorry, negative 1/24 times 0 minus 1, which will give you the positive 1/24. And that is the integral. Obviously, it's pretty long. It takes some time to figure out how to rewrite the general region into iterated integral, and then it's again pretty long to really compute it. Okay, so you are dealing with triple integral. It takes time. Now you can pause the video and try practice 1 through 3. Last, I'm going to tell you the other two types of the region. Pretty much the same thing. If you can sort of press the whole region on YZ plane, and you do have the projection, and also you have sort of the two ends, which means on each point you know how to express the two endpoints in terms of Y and Z. Or you press the whole thing, you project the whole thing on your XZ plane, which means for each XZ point, you know where it hits. So this part should be solid. The E, where it enters the E and where it leaves the E in terms of X and Z. Okay, then whichever works, that will be your most inner integral. Then the outer will just be the projection, which will be a two-dimensional region, which hopefully you can figure it out as our old type 1 or type 2 region. Then you do whichever you can. Fix X and see how the two ends are, or fix Y, see the two ends are, or maybe it's fix Z, look at the other two ends. Okay, so anyway, it really depends on the region. And so I will suggest the best way project it, and meanwhile see first, do you know what the projection is? Can you have a sense how the projection look like? Can you express the projection? Because that will be your region D that you need to do the x dy. Well, or sorry, not the x dy, the two outer integrals. And then the most inner one, can you really tell where it enters the region and leaves the region? That will put the whole 3 dimension together. Okay, that's it for this lecture.